the networking opportunities here at CppCon are well above and beyond any other C++ conference that I've ever been to.
Hi, everyone. My name is Saksham, and here to talk about reflection today. Okay, let's get started. I like this. Wait. Screens. Hi. Yeah, I like this title slide better. All right, so before I dive into it, I'll just take a brief moment to talk about why I'm here talking about reflection. So my name is Saksham. I'm the Director of Quant Research Technology at Tower Research Capital. It's a high-frequency trading firm based in New York. I spend most of my days agonizing over nanoseconds while trying to write some low-latency trading systems in C++. And the other half of my days, funnily enough, again, agonizing over nanoseconds, but this time while writing research systems in C++ and Python. My interest in reflection also has brought me to the ISO CPP Standardization Committee, although I am not a C++ expert by any measure, and I'm also a recent member of the committee. If you've seen any of my previous talks, I talk about Python and C++ a lot. This talk, funnily enough, will also have some mention of Python. But the general motivations that drive me are to write performant APIs that are also clean and highly usable by your maybe not so expert users. All right. So with that said, let's go talk about the talk. So this talk was previously presented at CPP Now, where I focused a little more on the basics of reflection, but I'm assuming people are kind of getting the hint that this is becoming a big deal. The people are a bit more familiar with reflection. So today we'll talk more about the interesting part, or the new part, which is all these reflection libraries. So the motivation for this talk is I actually ended up trying out reflection, and I ended up doing these 3 libraries that I'm very passionate about on my laptop with a functioning compiler that has reflection built in. And we're going to discuss the experience and how reflection-based libraries can look, but we will obviously spend some time discussing reflection. So let's get started. I'll have a lot of these AI-generated images, which have some metaphor for reflection at some times. Other times they don't. So cool. Reflection. It's the ability to write code that talks about the code you've already written. That's a vague definition. If you give that definition to someone who hasn't seen the reflection proposal these days, they would probably guess that, oh yeah, maybe I can write code like this in C++, and that would be called reflection. They would not be too far off. That is essentially the gist of it. But let's just distinguish this ability to write code about code from what we already have right now, which is metaprogramming. How's this different? I thought a lot about it. My answer is not so much. There's like a syntactic difference. So template metaprogramming was a system built into C++ meant to write generic code. We have sort of repurposed it. Some people might use the word abused it to do some stuff about, you can do things like stood if class v to check if a type is a class or not. And that's sort of very primitive reflection, but it's like there's some intersection, but again, this is like sort of an abuse of the template metaprogramming system. It wasn't meant to do that. And that brings us to the second difference between reflection and metaprogramming, which is if you build a system whose job is to work with you, the writer of the code, to help you talk about the code, that system will obviously be much better ergonomically. You'll be able to write much cleaner code. The compiler can give you more efficient data structures to operate on. And that bag of features is what we would like to call reflection for the rest of this talk. So there will be some overlap. Some of the functions you'll see is class v or type is class. They might look similar. The difference is the consistent bag of features. All right. So before we look at C++, I'll take a brief moment to talk about some other languages that already have reflections, so we know how other people actually use it, especially in languages that are heavily used. So I'm going to focus on Python, Go, and Java. I know there are other compile-time languages that have reflection that works similar to how C++ might have it, but these languages are used quite a bit, so this is like a vote of confidence that it's a useful feature. So of course, my first one would be Python. Reflection in Python lets you do a lot of things. Some of these things seem obvious, like you can access the class's layout. It also lets you instrument function calls, which is, again, believable. It also lets you add and remove methods or attributes from your objects, which almost starts getting into crazy land, especially when you see the kind of things that people do with it. And as an example, I have this very small snippet where there's a function modify class. It checks if your class has a copy function. If it does, it wraps it with a wrapped copy that is adding some prints. It's also printing all the attributes of your class. And then it's just replacing the copy function with this new wrapped copy. As you can see, it works. And you can call wrapped copy twice, sorry, modify class twice, and it would just instrument this copy function twice. Pretty lean API, I would say. Golang is a compile language, but funnily enough, ergonomically, it's going to feel very similar to the Python example, mainly because it's a little more duck-typed in feeling than it is compiled. That's my personal opinion, but yeah, they provide a runtime reflection package which lets you create these reflection information values at runtime. And again, as an example, you can operate on this struct. This code is not very beautiful, but it's from their blog. And you can print all the attributes or members of your struct, and it works just fine. Lastly, Java, again, a highly compiled language, but since it works in a VM, should not be a surprise that this would also kind of have this information about your type at runtime, rather than like, as a compile time construct. And that's exactly what this feels like, similar to Python and Go. Here I also have a snippet where you can actually just like kind of fetch a type based on a string. Like you can just say, hey, like I want this class whose name is this, and you get a representation of that class, which is just crazy. Like, you started with a dynamic string and you can access a type. It just feels very different from the things that we're used to in C++, right? So this is scary. You think of runtime costs and strings to types and just, yeah, we don't want that. We've done RTTI before. We're scared of this stuff. And luckily, zero cost abstractions is a good philosophy in C++, but the best thing is const eval has progressed far enough that we can actually do a lot of things at compile time in C++ without template metaprogramming these days. So we're going to lean on that and we are leaning on that to build on reflection in C++ and hopefully for CPP 26. And that is this paper P2996 that's been discussed quite a bit over the last one day, I guess, but also it's going to be discussed over the next X sessions that are on reflection in the coming few days. So this paper, okay. All right, yeah, this paper is by a number of great authors. It's progressing pretty well through all the C++ standardization processes. There's been some good progress at St. Louis. Hopefully the progress continues, and it's looking promising. It did not come out in a void, though. There has been a lot of work before this on reflection, which is why some people are kind of apprehensive about whether we're going to get reflection, because we've been in this state a couple of times before. But it's looking promising this time. What do we have with this? We don't only just have a design, we have two working implementations. EDG has an implementation on Godbold. Bloomberg has a fork of Clang that's available on Godbold, as well as GitHub. You can actually download it and compile it. Here's a Godbowl link with some code from their proposal, working on both the compilers. It's the enum to string example. So how does this work? The first thing that this paper adds is a reflection operator. It's a unary operator that takes various language grammatical constructs, like functions, types, namespaces even, and it lifts them into some magical reflection land where you can do things with them. That's why I like this operator. It's very poetic. It's kind of lifting things. You might hear talk about a slight reworking of this operator that seems to be under debate for various reasons that this talk will not cover. I don't mind it personally. I think it looks equally poetic. Yeah. I do like it more than like a keyword, like a reflex per or something like that. So yeah. All right, the next thing we have is this thing called std_meta_info. So if you notice in the example, like the function that we're passing this reflected thing into, it takes this object of type info. So this is a formless type. It has no accessible attributes or something that you want to use. All this does is contains some sort of internal pointer into the compiler's implementation. You could just assume that. So you're not going to actually call its member functions or access any attributes on the std_meta_info. We're going to use some functions to inspect this thing later, but that's it. We also have this new thing called a splice operator, which takes that std_meta_info and kind of pastes it back into your code. So whatever thing that it points to inside the compiler, it just takes that thing and puts it back into your code. So as an example here, I can make a std_meta_info of a static member variable of my struct, and I can just print it later. And of course, that std_meta_info could have come from any other constant expression as well, and that would have worked. This is the crazier part. We also have this new feature called define class, which lets you take an incomplete class and provide a specification of some members you want to add to that class, and it'll just define that class for you, almost in thin air. There's various different ways that people are proposing that this be done in other proposals. This is the approach that is in the paper P2996 right now. And this solves like a lot of the primary pain points that C++ has had. So I think it's still good, even though there might be something that supersedes this later. But hopefully this is explanatory enough. We're saying we need a class S with two data members, I and J, right? It's the equivalent of this. Yeah. And finally, as I alluded to earlier, there's a lot of const_eval methods to go with this. So the std_meta_info object itself is formless. You don't do anything with it. But you can pass it into all of these const_eval methods that are now available with this proposal in the language that you can, in the standard library that you can use to do useful things. So if you're going to be writing some reflection code and you want to say things like, if this thing is a function, then instrument this thing with some prints around it. So you would use the is function. There is way too many of these functions to list on this slide, but here's a few salient ones. So now that we've kind of established what reflection is, I just want to take one last brief moment before we go into libraries to talk about how is this going to change our world? How is this a useful thing? And for this, like, the paper does a really good job. It has a lot of useful examples. I'm going to just take those examples here. The first one, and I think everyone's favorite, poster child of reflection, and our favorite thing in C++ that we cannot do today, enum to string. This is how real reflection, proposed reflection code looks now. You say things like, if you have an enum value and you want to convert it to a string, you can list the enumerators of that enum type, and you can check which of those matches the value that you're looking for, and you can return the string of the identifier of that enumerator. If you squint at this code hard enough, you're going to notice this template for thing that I put here. And the proposal uses this a lot. It doesn't exist. This is a separate proposal called expansion statements. But luckily for us, the proposal itself is complete enough that you can replace this guy with this other thing, which is a helper function called expand. And it feels almost the same as the thing we just saw, if you want to see the thing again. All it does is it replaces the for loop with a function that calls a lambda for each element in the for loop. It ergonomically feels almost the same. It works pretty well with the const eval kind of operations that we're going to do. So I will use these two syntaxes interchangeably throughout the slide. And I think the proposal kind of does as well. So the next thing is a command line parsing. I philosophically just see this as another version of serialization and deserialization, where you have some struct and you want to, take some input string or something and convert it into that struct, or convert the struct back to the string. So just looking at command line parsing should be enough. And as you can imagine, this is also a very similar operation to the one we just saw. You just loop over all the data members of the struct. You see if the command line contains any flag which contains that data member, minus that data member's name. If it does, then you parse it in and you populate the struct. If you look at line number 6, there's a splice operator to fill in that data member into the struct directly. I should have had a highlight for that. And yeah, and this kind of works. This is a very simplistic command line parser. There are much more complicated ones that are possible with reflection now. And the last one is arrays to structs. Struct of arrays, where people who might want to define a struct like a point, but for cache efficiency reasons, maybe they want to keep all the x coordinates together and the y coordinates together. So this is a fairly common operation in like geometrical applications and so on. And this is also trivially done with the define class approach that was described earlier. You go over the old members, you construct the new data members, you create a spec of those, and then you define that class and return that. It looks a little dense, but after you see a couple of these things, all of this starts seeming very similar. So this is pretty nice, right? We're convinced we can do a lot of things with reflection that are really good. These are some primitive things. So now we have a new superpower. How do we actually make this, use this in a form that makes the language better? And of course, people have been talking about this quite a bit. The answer is libraries. This is a really powerful language feature, and the design motivation for this feature is that we should add this one feature that rules all of the other use cases that have existed, that used to be added into the language every time we wanted to do something new and cool. We're solving way too many things in one go. It's a powerful feature. We have a reason to be excited about it. And the way we're going to use this is to write amazing libraries. Other languages have had an edge over C++ on this front for a while. Like, if you're a Go user or a Python user, you just go and write like argparse or something, and you already get a great command line parser. In Go, you get awesome serialization, deserialization support out of the box. And they've had that because they've had runtime reflection for a while, and obviously in C++, we're not going to do that. But with compile time reflection, we're finally getting there. And we have to use this power to make sure that our beginner users and business logic writers are able to have a much better user experience. So as I said, our goal should be to target these two categories, and make sure that as library authors, we're designing APIs that force people to not even look at reflection. So your actual user should not even know that you're using reflection under the hood. Your libraries should be so good. And this is possible, hopefully. I mean, from experience, it will not happen until, I don't know, a decade from now, but it's possible. So on this point, let's do some actual library design to see how this might work and how the future might look. So as I alluded to earlier, I'm going to do 3 different libraries. The first one is Python bindings, automated. The second would be some sort of a type hash That is like a hash that represents the layout of a type. And the third is the one I'm most excited about, which is a where_std any with some sort of duck typing. So let's get started. First one, Python bindings. So in case, so my last year's CppCon talk was about Python bindings, and that was before I got into reflection. So this is a good full circle. The problem statement is that we have some C++ types that we would like Python to be able to access, manipulate, mutate, anything. And the background, if that statement didn't completely make sense, is that C++ and Python can run in the same process, because whenever you're running a Python script, you're essentially running a C program that's reading your Python script. And it's possible for Python to be told how to interact with C++ types and access their internals or call methods on those member functions on those types, and so on. So that's the summary. And the way it works is, let's say you have these structs or types that you want to expose to Python. Perhaps you want to access this item and row kind of objects in Python. This is an example from my last year's slide. So if you wanted to do this, currently the way to do it is to do something of this nature. Obviously, this is super verbose. We're mostly repeating ourselves. We're really just repeating ourselves for the most part here. There's a few places where there's some, art involved. Like if you look at the items function, there's a return internal reference thing. Sometimes you want to configure what to do if you're returning a reference object. Should we make a copy of it? Should we make a pointer to it that has a shared pointer to the parent to ensure lifetimes? All those crazy things. There's a few of those things you would need, but not always. Most of this is just completely repeating code. What we aspire to is this, hopefully. With some customization, that would be great. But of course, with reflection, as you might guess, this is easy peasy, maybe not. So let's walk through this quickly. So I'm making a function called makePythonType that, first of all, it just takes the name of your type, the identifier of your type actually, and calls that the class name. And it defines a Python class using the boost Python syntax that I just showed. It's not relevant which syntax we use, but they're all similar. We define the Python type object. Then obviously we're going to loop over all the public members of the struct that we're trying to expose to Python. Then we can check if that member is a non-static data member. Then we want to allow Python to read or write to that data member. I'm sure we can do something like a const checking here to tell Python not to write it if that data member is a const data member. If that's a function, and perhaps not a special function, then we can kind of add some handling that, okay, tell Python that it should be allowed to call this function. We provide the pointer to the function. We provide a name of that function. And here, just as an illustrative example, since this is a toy example, I've ignored cases where the function returns a reference type because we want to customize that later. And that's it. Not too complicated for a toy example. This one is a toy example. And the reason is we still need to add customizations to this. Yeah. We've already discussed a couple of customization things like reference handling and names of classes and so on. You might also want to add doc strings, for instance. Python loves doc strings. It's not super easy. There's a paper that discusses this, P2911 by Jagrat Dev and Adam Lab. It mentions this one approach, which I don't hate too much, which is that you just list a bunch of customizations and you let the Python binding library apply these customizations at the time of declaring the Python. That paper also discusses an alternative approach, which could exist in some future C++ version, if someone wanted to propose that, calling it user-defined attributes, where you could annotate things at the point of definition as opposed to the point of use. So this is slightly different ergonomically. You require access to the source code of the class that you're trying to bind to Python. So if you don't own the header to that class, it's perhaps coming from a third-party library from a package manager, then this approach would not work for you. The other one would. So there's some room for both of these. A digression on this. There's some precedent for this user-defined attributes thing in Golang. Their entire serialization, deserialization ecosystem is built around these very nice, pretty backtick annotations. And that's why the general beginner user experience for these kind of things in Golang was pretty good, at least back when I used to write Golang. Cool. So a summary of this topic. Customizations are still repetitive, but other than that, the basics of reflection can be done. So this was a simple library that just works. A lot of people have had to write Python bindings before. Hopefully, the new age of libraries that we come to can deal with that better. Let's move on to the next library, ABI hashing. So that's a vague name, and I'm going to set the stage for that. So let's say you had the ability to hash a type's data layout or its memory layout. What would you do with it? And here's the problem statement. Let's say you're sending data between some X processes interchangeably, crisscross everything. Or perhaps one process writes some data to a file and the other process has to read it. Oftentimes, you kind of want to add some header to the data that says, oh, this is the schema of this data that I'm sending. And in the general world, if you don't care about performance too much, you might use HTTP, JSON, all that to represent your schema directly. If you're sending binary data, that often doesn't work. So perhaps you want to minimize the header size, the schema type that you have at the start. Here's an example of why this might be useful. Perhaps you have some server process that's listening to data, some binary data over UDP. And you've upgraded the code and you've changed the schema of the data you're sending. But one of the publishers of this data is still publishing the old schema. So this is obviously bad, corrupt stuff, everything. So you might ask, okay, let's send the schema in textual form. That might take up some space, but it's a completely valid solution. You still want to be able to walk over the entire memory layout of the data you're sending. Perhaps you have a struct of structs. You want to describe the layout of all the structs that you're sending. And ideally, you don't want to waste too many bytes doing that because this is just metadata that you're going to end up comparing. Also, you might have to send that data across on every message that you send over. It's lagging. Yep. Right. The second use case, which a lot of people might actually find usable, is what if you have multiple .so files that are being linked to by your executable, and those .so files are built by two different processes, and they want to send some data in between across each other. So as a visualization, on the left-hand side, I have something called libcreator.so that creates some object of this class, my class. And on the right-hand side, I have some libusermodule.so, which uses it. And it's possible that the user module is coming from some open source package that I downloaded, so I cannot rebuild it. But I want to create more objects of that my class type. Like it's a virtual class, so perhaps I want to extend it and make my own objects of that class. And I want to send it over to this user module on the right-hand side. There is no uniform way in the language right now to give some sort of, I don't even need 100% guarantee, some sort of 80% guarantee that the two types in the two different .so files are the same. You could add a version field into that type, but obviously, we all love to forget updating things sometimes, especially when things are updating transitively. And of course, let's say you had a Python binding library. It could not do that generically for you. So in the previous example, if the my class type was exposed by both .so files, the Python binding library could not actually look at them and automatically inject some sort of version string, because version strings are just manually done. So I say let's try to create a hash of the types layout. Obviously, with reflection. Yep. So again, this is going to be a more decent test of the abilities of P2996, because we're going to iterate over the entire layout of a type. And it's important to have complete coverage, because otherwise you're missing out on information that could affect the layout of the type. This is actually one of the first things I did with reflection when I got into the conversation. And of course, hashes they need some sort of configurability. People might say things like, I need to hash the names of data members. I don't need to hash the names of data members. I want to include virtual functions. I don't want to do that. So perhaps there should be some struct that represents some configuration on the hash. Here's a test case. It's some order struct. And then there's a mylist, which has a bit field in it. It's a template type. And then there's an order book, which kind of has that same thing twice. The API will probably look like the bottom one. That one works much better, because now the way we're proposing reflection be used is with const eval methods. And the core of the code looks like this. So let's go over this quickly. First thing we do is, of course, we need to check if our class inherits from any other classes. So let's hash those classes recursively. Then we go over the non-static data members of our class discussed earlier. Yep, similar to the Python binding one. And we check if the type of this element is an indirection or not, if it's a pointer or a reference. And the user probably doesn't care about pointers or references, because maybe they're sending it over the network, at which point you might want to just raise the question, why do you have a pointer in a struct that you're sending over the network? But you can check that this way. You can also access the names of all the data members. You can hash them. By the way, I forgot to mention that I found a compile time hash combine function on Stack Overflow. It seems to work fine enough for the use case here. Yeah. Then you can access the offset of every data member. There was some debate on this as to what thing should be returned by this offset of element. And the idea is that if you ever find yourself using offset off, you would probably also want to access the bit offset and not just the byte offset, because if you don't do it, you just accidentally broke your code for bit fields. So we do that here. The next thing you do, you check if this data member is of some other type. So you take that type and you hash that again. And at this point, you're probably wondering that we better have some sort of caching. Okay, with that said, let's say that isn't a type, isn't a class. So it must be some sort of a pointer or a reference or a primitive type. If it's a pointer and we want to hash it, then we actually remove the pointer. We can do that with the reflection API. There's a function called type remove pointer. You get the type after removing the pointer, and you hash that type. For reflections or references, it's the same. And the last thing that remains is primitive types. And this part is slightly funny, because primitive types don't really have a standard identifier name. So the reflection proposal has been going back and forth on how you would name different types. Like even bool, for instance, is not going to work if you pass bool to meta identifier off, because bool is not an identifier. So there will be some libraries that come in place here, and they give like a standardized API that, oh, you give me a type, a primitive type, and I'm going to give you a standard name. The reflection proposal has moved away from promising very standardized names for things. But yeah, there it is. This seems to work. It works fine. Did we leave anything out? So one thing we left is that we should probably hash the size of the type as well, because there might be extra padding at the end, and we might want to subtract the parent size as well. And we should also avoid cycles. This is pretty important if you have pointers and forward declarations. Seems doable enough. You just use ranges and vectors and keep a list of all the types you're hashing currently, and just general graph traversal stuff. Just for the feel of it, you can also see how this code used to look in the template metaprogramming world, similar code, where instead of keeping a vector of these std meta info things, you would keep a variadic list of types, and you would have to use boost mp11 to check if the type you're hashing is inside that type. This code also works, but obviously we're kind of moving towards a much better world now, so that's pretty awesome. Okay, so what do we have now? Have a way to check compatibility of types across processes without using protobuf. Everyone just uses protobuf for this stuff right now. It also solves 80% of the use cases. I don't know, maybe 20%. We can pick a number here, but the thing is that if I wanted to write a Python binding library, it could do some sort of safety checks when I'm sending class objects from one type to another type, one module to another module. It doesn't require too much work on the user's end, but hashing is still a funny choice, and it's more a matter of choice as to whether you want to hash the type or you want to just represent the type as a schema or a JSON. You could do that with the same techniques that we just went through here. You could even populate schemas like Apache Avro or even protobuf with this thing so that you can get some cross-language interop. So yeah, that's it for the ABI hashing topic. And this brings us to my favorite part of this talk. And this is a Pythonic std any, and I promised you Python, so here it is. So this is the third library that we're going to discuss today. I'm a big fan of this. I'm loving how it feels. The motivation for this actually came from Boost Python's 20-year-old documentation, where they had something like this working. Now, this obviously uses Python's internal infrastructure. This object is a Python object type wrapped with a Boost Python wrapper. But this feels very interesting, right? Like, if this kind of code worked in C++, like some beginners or like some business logic where you don't care about performance would become much easier to write, perhaps. At some point, we added std any to the language, which also works pretty well. It does something very different from the thing we just saw. It doesn't have any sort of duck typing. You kind of have to convert the object back to the original type that it belonged to. But at least we can do something with it. And of course, this uses runtime type inference information, so we're kind of, not everyone is happy about it. But so the idea was, why don't we take these two things and use reflection to make something called virtual any. Calling this virtual any because hopefully it can contain virtually anything, but let's see. So the example is, let's first look at this and see. If this worked, it would be pretty cool, right? I have an object A, and I can assign anything to it, and I can call attributes on it dynamically with a runtime string. I can call a method on it with .call. I can say do quack, and it does quack. It would be pretty cool, right, if this worked. Some people might say this is bad. There was a talk at in a New York C++ meetup by Gasper, who at some point said, what paradigm is C++? All of them. So, I mean, why not this one? We should have all. This kind of thing is called duck typing, where you say if it quacks like a duck, might as well call it a duck. So let's see if we can do this. All right. We can, obviously. Otherwise, this would not be on the slides. So the idea is we make this thing called the virtual any holding class. And what it does is it just holds a shared pointer to something called the virtual any interface. It's a controversial choice, but for the next, let's say, 10 minutes, not talk about performance. We can talk about it later. Yeah, so we keep a shared pointer to something called virtual any interface. And if you haven't guessed by now, virtual any interface, you add some accessors like attribute, you add a call function, which has a variadic list of arguments that you can pass to it. This is not going to work directly, and we're going to have to put some work into it. You can add any stream operators that you want to add. You can add operator plus, minus, all that. I haven't done that. You can add some controversial methods that, again, are going to give you the feel of RTTI, but they might. So let's see. And if you haven't guessed by now, the virtual any interface is a virtual interface. It would be the one that implements all of these things for each type that you're making a virtual any of. Yep. And that we would implement with the reflection. And funnily enough, even though it sounds like code generation, we're not going to need any of that define class, code generation, tokenization, all that stuff. This is going to be simple reflection as it is in the P2996 R5 paper as of today. This code works without any further proposals. So let's see. This virtual any interface has to be extended for each type that you make a virtual object of. So in the earlier example, I made one for int and one for my duck. So this interface has to go and implement these functions. You could add allocators on this. I'm not going to do that for the purposes of this slide, but might be interesting to some people to figure out how to manage the memory. Okay. So the first thing you would do is we want to focus on this .adder function that I showed that lets you access attributes of this virtual any object dynamically by just passing in a string name. And to do that, you first check if this thing is a type. If it's not a type, then it doesn't have attributes. So why are we even doing this? If not, you go over all the non-static data members, and you check if it's a public data member that has an identifier. Otherwise, why are we doing this? You check if you've already set the result object. The result at the top is a virtual any, which I've implemented with a Boolean in there, which tells you if it's valid or not. But you could very well write it in a way that you have a boost option there, and you disallow an invalid virtual any. Then you go and check if that element is the one you want. If it is, then, well, we're good. We set the result and move on. How do we do that? Since we're in a function which is behind a virtual interface, this function's return type cannot be a template type. So the return type has to be a virtual any again. So in this case, what I do is I make a virtual any of that attribute and of that type. Again, controversial, but as long as we remember we're writing Pythonic code, we probably don't worry too much about it, and we can worry about those things later. Finally, we can raise an exception if we did not find the attribute. So this works fine. We can also implement operators. In this case, I ended up implementing a stream operator, so you can just print each type, or you can at least print the name of the object if there was no stream operator. So this kind of lets you print any arbitrary object if you make it a virtual any. And there it is. At least the most primitive thing works. You can access attributes dynamically now. Now on to member functions. They are somewhat harder because they take arguments. And we're doing some sort of type erasure here. We don't actually keep the type information at runtime. So what if I want to make this work? I have two methods here, doQuoc nm and doQuoc nvirtual that take some arguments. And then I have the doQuoc, which doesn't take an argument. So let's first handle functions that do not take arguments. This is pretty simple. We make a type callable, which can save the function and its arity. Arity is the number of arguments that the function takes. You can loop over all the functions. Members of this type, you can ignore the non-public ones and all, same as before. You can check if the thing is an incorrect name, then you don't want to care too much about it. Okay, now let's focus on, we want to just filter the functions, member functions of this type. The reflection proposal allows you to do that in a complete manner. The proposal is complete, that it lets you describe all the constructs of the language. We hope that's what it does. Okay, so as I promised, first we're going to check functions that do not take any arguments. So we use concepts to check if this code compiles, if the code function with no arguments is a real function. If it is, we use some old school Jekyll type to get the return type. And we make a lambda that takes some arguments of type std, vector, virtual any. We hope that no arguments are passed here. And this lambda actually just calls the function and returns the value as a virtual any. So this kind of works. Now you can call any function on your class that does not take arguments. You might guess that the lambda I have here takes an argument which is a vector of virtual any. So you might guess that to support arguments here, we're going to convert all archetypes that you pass into a vector of virtual any at some point. And then we're going to have to convert those virtual any's back into the archetypes. And this has to go through a virtual interface, and that's why we have the virtual any in between. So here's an illustration of this. The snippet at the bottom, it tells you that, okay, yeah, even though you can give the call interface and it can take any arguments of any types, at some point we need to cross the virtual boundary. So you will have to convert those types into something that is a uniform type that goes through the virtual interface. To get the types at least, there's another paper that's coming up, P3096, that lets you get types in a more reflection-friendly manner. But you can use old school C++14 kind of stuff from boost callable traits and all to get the function types. So that's what I did for now, since I want to make sure that all the code compiles here with the latest proposal. So runtime virtual interface means we cannot use the template types. And as you might guess, that at some point you need to convert the virtual any back into the original type. And this should give you some sort of hint that RTTI is coming in, something like dynamic cast. We'll see. Okay. So it's the same code as before, except that now we're getting rid of the assumption that the function needs to compile with no arguments. So, as I promised, some boost callable trait stuff to get the argument types of this function, access the arity of the argument types. And we replace that lambda with another lambda this time that converts the virtual anythings back into the original types, since we have the original types at this point. And then we have to write something like apply invoke, which is similar to std invoke and so on, that takes a list of these types, that takes a tuple of these arguments and calls the function on that object with these arguments. This is general C++ stuff. Disclaimer, this was written by ChatGPT, but it compiles. Yeah. So we had this magic method here, get arg from any vector, which seems to convert a vector of std any, a virtual any object back into the original args type. So obviously we need to convert a virtual any into a given type. We need that functionality. Let's leave that aside for a second and let's just focus on this function. What it does is it makes sure that your vector is of the same type, same length as the arg types that you have to pass to your function. If it is, it copies the vector into a std array. And then we write a compile time function, which converts a std array to a tuple of that arg type. And this tuple can be passed finally to the function that we have. This is, again, more std apply stuff and some variadic argument type list, old expressions. It works. Take my word for it. All right. So the last piece that remains is this thing I have here, which is virtual any cast. And now this is similar to std any cast. Okay, so let's see how this could be implemented. It sounds like RTTI. Unfortunately, at least in the implementation I did, it is. It's pretty easy to do if you assume RTTI. You just do a dynamic cast from virtual any to the virtual any impl of the type you're trying to cast to. If that works, great. You can also choose to handle dynamic casting to reference types and pointer types, and just to make sure that things are working fine. And you can do some sort of implicit conversions here. And if it doesn't work, you can raise an exception that, hey, you passed an argument of a type integer, we needed a float here, and so on. So it works at least. And as promised, this code works completely fine. You can call functions with any number of arguments. This also works with reference types, but that's doable. You can believe that because all you need to do is handle perfect forwarding. So this code works. There's only one issue here. We used RTTI, and the moment we say RTTI, we're dead in the water. So do we have any other ideas? So this part of the problem is actually the same one that std_any probably faced as well. So I went through their page and I read up a little bit about why they did things the way they did. To do things in the most general fashion, like to provably confirm that this object was of the type that you wanted to cast it to, then RTTI is one of the only options we have. I do want to talk a little bit about some other options. We just talked about ABI hashing like 15 minutes ago. And perhaps that's a way to actually do some sort of safe, semi-safe validation that you're casting an object to the right type. If you hash the type and store that type in the virtual any impl, if you did that, you have sort of carried some runtime type information, but you've only carried it for the objects that you care about. So this is zero cost abstractions compliant, unlike RTTI. Unfortunately, you can have hash collisions, and no one wants code that can probabilistically do undefined behavior. So that's bad. I also thought a little bit about another approach that has no false positives, which means it should be good enough for this purpose, which is that you can make a function. It should not be an inline function. You can make a function that defines a static for each type and returns the pointer to that static. And under some constraint conditions, this can actually give you a unique uint64 or const void star for each type that you have, as long as the linker makes sure that they get merged. And this is also ODR compliant. It should not have false positives. And perhaps this is one way to bypass these issues, especially if you're implementing something like this virtual any in a non-RTTI environment. So I don't know of any downsides to this thing. I'm happy to hear if people have any, but moving on. Yeah, finally, just some discussion on this. Obviously, this is slow to run. This is an experiment. This is slow to compile as well. You can do it properly, and then it wouldn't be too slow to compile. Function calling API is a little limited. You have to move everything into, you cannot do implicit conversions, and you have to put everything into a virtual any, but it works fine. And it works as of the current implementation. There's a Godbolt link for this as well. So what is this? It's definitely a very strong experiment with reflection. It also allows you to make some cleaner inter-module APIs and DSLs. I'm looking forward to something like this. I want to be able to write simple code sometimes, and I don't want to annotate everything with types. And this should be helpful, especially because, make anything into a virtual any, you can print it, you can pass it into some diagnostic functions and so on. So I could have diagnostic printers that can do a print for any virtual any. I did skip over object lifetimes. Python spends a lot of time dealing with object lifetimes. If we wanted, we could just borrow Python's machinery to do that, or we could re-implement that. We know for a fact that it is doable since Python does it, but there's no immediate blockers on that front. So yeah, that concludes the section on virtual any. And this leaves us with just a few more minutes for the last section, which is, we've been talking about reflection a lot, but how have we been working without it for so long? And just a slightly different topic, but I think the most common thing that we've been doing without reflection so far is this thing called human reflection, where we just manually type out the same thing over and over. Works fine. We're worse off because of this. We can do new fun things with it now. The other thing we've been doing is forced in. If you saw Herb Sutter's keynote talk on Monday, there was a lot of things about how forced in actually introduces extra build steps into your process, and that is obviously worse. But we have to live with what we have. People have their own versions. The two that I'm familiar with are Protobuf and Avro. What they do is you write some custom DSL on the left side, and it generates some C++ code for you that I have on the right-hand side that you can use in your application. This is an extra step in your build process, but it is what it is. There's a similar one for Avro, which is by Apache. Also a very similar situation. I do hope that with reflection, we can generate these kind of DSLs from our C++ code, so we don't have to write things in multiple places, and we can get inter-language operability as well. This is the most modern form of reflection that we use, which is my favorite one. This is how I do command line parsing with LLMs, so I don't have to type it out. But it works pretty well, honestly. Yeah. And of course, there's some other approaches like clefdisk, and there's some old school metaprogramming tricks for some semi-reflection that works. So yeah, with that said, that concludes the talk. We hope that C++ gets reflection. It's hopefully not too complicated, and let's get hyped up. All right, thank you, everyone. Right. If there's any questions, I can take them now, or. Okay.
Great talk. It was really interesting. I really like the section on the virtual end.
Thanks.
One question for you there. So, yeah, we have that issue of the virtual boundary. Obviously we can't have template functions on the virtual interface. So yeah, we have this problem of we have to pack all the things up into virtual ennies to pass them over the virtual boundary to then maybe just find out that they were the wrong types after we do that. And so my question is, and I have no idea, but would it actually be possible for us to implement a function on the virtual interface that basically says, can I handle this call, and then actually pass through a vector of meta info or something like that? I don't know how the meta info types can be used, but it would be kind of interesting to answer the question, can this type even be handled before we take the expense of actually packing them?
That's a very good question, and unfortunately the answer is no, and the reason is std meta info is a compile time construct. It contains pointers to, this is my mental model, I might be wrong, that it contains pointers to the internals of the compiler that represent the thing it's talking about. Mm-hmm. The thing that you need at runtime, if you need that at runtime, that's just RTTI and type info, so we're just back into that same problem again.
Right.
But I'm sure we could implement a slightly more efficient failure mode using type info if you have type info.
Right.
And yeah, that's certainly possible that if you could implement a method that says, hey, I have these types, will you be able to handle them? And but it's a failure mode, so I guess the performance of that is sometimes a bit subjective. Yeah.
Thank you.
Yeah, thanks.
Hi, thanks for talking about it. I'm very excited for reflection. Do you have any idea what debugging this stuff looks like? If I forgot something, neglected something, how do I figure out what I did and how to fix it?
So that's a very good question. I intentionally skipped debugging here.
Okay.
So what happens is that if you do a reflection for something that isn't a valid thing that you can reflect on, or if you're trying to call a reflection const eval method on something like identifier of of something that doesn't have an identifier as an instance. The compile time error you get is that this thing is not a constant expression, which is a very convoluted way of saying it's an invalid reflection, but that's how the standard can handle these compile time reflection things in a form that is palatable to the standard as of right now. I would imagine that this should be workable at the tooling level at some point, that it should be able to identify that it's not a constant expression, and perhaps your compiler can tell you that this was a reflection that you're trying to do that was wrong. But at that place, I'm speaking out of turn because I am not a compiler implementer. But yeah, the experience has been, it's not the worst thing in the world, but you do struggle. I think there's a learning curve with the whole const eval thing and constant expression stuff, which is a little new because now there's new ways to introduce non-constant things that look constant to you.
Thank you.
Thanks for the presentation. And I have one question regarding reflecting on functions. So I can be wrong, but I think for Python, like it's possible that like we manipulate the function itself. For example, like we can transform a for loop into something else. I believe that's possible. I can be wrong here, but like anyway, for C++, I'm wondering like if we consider the similar like case, like for example, we suppose we have a function. We know that we want to avoid copy when possible. Like we can do, if we can reflect some functions, we can like analyze the whole function and replace all copy with move when possible. Right. So I'm wondering like is a committee considering such use case? I know this must be more complex, but like I think it's something that's beneficial. Like basically we can implement our own like optimizer for compiling.
So
this, right?
that's a very interesting thought. I think like the reflection as a concept generally doesn't talk too much about parsing existing code, because that's more like a parser's job. And I suppose reflection theoretically could include, a way to read the function and then rewrite the function. We will have the rewriting part that is being proposed in a separate proposal, that you can just generate any code and put that into your code using reflection. The hard part here is going to be reading the existing function, because reading a function involves parsing. And the moment you make parsing a usable thing, like someone can write code that can parse their code, you have kind of restricted the language from ever changing its syntax. And you don't want to do that. This is my take on it. So generating code would be fine, and that's being considered. But reading and parsing existing function body is probably, I think, out of scope for the time being.
Thanks.
Thanks, Saksham. So can we also access private members?
Yeah. Yeah.
So that is security thing?
People have raised that concern, yes. Hopefully this is at compile time. So it's not that you're giving a struct to someone and they're calling things on your struct behind some object boundary and they're able to access those things. That would be unlikely.
It's strictly only at compile time.
Yeah, all of this is compile time. All right. There's no more questions. Thank you, everyone. Thanks for coming.